Every product eventually faces its first cold start. It's the moment theoretical assumptions from a climate-controlled studio get audited by harsh physical reality. At freezing temperatures, the physical symptoms are immediate. Lubricants thicken, polymers stiffen, digital screens lag, and battery output sags. When an electric vehicle loses range in the winter, the popular story almost always points the finger at the battery, blaming cold chemistry for the failure. The official numbers seem to support this at first glance. If you drive in mixed conditions at 20 degrees Fahrenheit, your vehicle's range drops by roughly 41% compared to a warm day. But treating that drop as a purely chemical failure creates a blind spot. It masks the actual root cause of where that energy is going. To find it, we have to look at winter testing data from the Department of Energy and the EPA, administered by the Oak Ridge National Laboratory. This chart compares that initial range drop against a second scenario. If that exact same vehicle turns its cabin heater off, the range loss is shrunk to 12%. Looking at the delta between those figures, 2/3 of the energy loss in the cold has nothing to do with moving the car. That massive slice of energy is being spent entirely on warming the several cubic meters of air surrounding the occupants. Warming the cabin is a challenge settled through spatial and architectural choices. For 100 years of automotive design, engineers never had to budget energy for cabin heating. A traditional petrol engine converted roughly 20% of its fuel into forward motion. The remaining 80% was expelled as waste heat, and the cabin heater was just a tap plumbed directly into that free rubbish. An electric drivetrain works entirely differently. It can convert up to 91% of its stored electrical energy directly into moving the wheels. By achieving near-perfect mechanical efficiency, engineers inadvertently deleted the exact byproduct that used to keep you warm. Without that combustion waste, heat stopped being free. It became a heavy electrical load that has to be drawn straight from the primary battery. And the timing is difficult. This maximum heating load hits the system during the exact season when freezing temperatures are already restricting baseline battery performance. The automotive industry's default reaction has often been brute force. Just install a larger, heavier battery pack to compensate for the loss. But hauling around hundreds of extra pounds of lithium year-round just to warm up air in January is an expensive, inelegant engineering compromise. You cannot solve what is inherently a problem of packaging and spatial thermodynamics by just throwing more chemistry at it. The only elegant answers to winter range loss are architectural. They required the precise allocation of physical space within the vehicle. Take cabin insulation. Thickening the walls holds the heat in, but that extra section thickness directly competes with the interior room available for the passengers. Then there is the glass. Maximizing the greenhouse for fashion or a panoramic roof creates a massive thermal leak that actively fights any attempt to retain warmth. Directly heating surfaces, like the seats and the steering wheel, is highly efficient because it warms floor layouts and careful thermal loop planning. None of these dimensions, the packaging space for a heat pump, the insulation thickness, or the glass area, can be retrofitted later. There is no options box called warm. When you remove waste from a system, you simultaneously starve everything that was quietly surviving on that waste. Technological efficiency always arrives with a hidden invoice, and that invoice is usually presented during the first freezing week of the year, rather than on the specification. That thermal invoice is either successfully budgeted for or permanently defaulted on during the very first weeks of concept sketching. By the time anyone points a camera at a finished concept car for a studio photograph, its true thermal and aerodynamic fate is already locked in place. These invisible trade-offs, where insulation competes with volume and glazing conflicts with the thermal loop, cannot be resolved by an aesthetic sketch alone. Success depends on interrogating the thermal reality of a shape before the first model is ever cast. To design for the first cold start, you have to see every angle before you build.